Hello everyone and welcome to this week's episode of Lecture Tuesday, where we'll be talking about common ignition strategies in spark-ignited internal combustion engines. To explain the cycles of the IC engine, basically, the internal combustion engine is based on 4 thermodynamic cycles, of which take 2 reciprocations of the engine to complete. These are the intake stroke, where the piston is pulled down, creating a low pressure region which facilitates the fuel entry controlled by the intake valves. And then the piston starts its upward motion, and with the intake valves closed tight, the mixture undergoes a compression as it's squeezed between the piston and the cylinder head. Now comes the combustion part, which can be initiated via different sources. The combustion creates a burst of energy, pushing the piston down and delivering work. And finally, once the piston has reached its most bottom location, also known as the bottom dead center, and starts to transition towards the upward movement, the exhaust valve starts to open, assisting with the escape of the combusted gases. All of this can be seen in this small animation here, which shows the piston pulling in fresh unburnt fuel mixture, pressurizing it, and then combustion happens and work is delivered. And finally, the combusted gases are exhausted out with the exhaust valves opening. What are the most common ignition strategies? Well, these can be generally categorized into 2 main groups, which influence how the mixture is combusted, and usually each group works on a specific type of fuel. First, we have the compression ignition, also known as the CI. Compression ignition can work on homogeneous charge compression ignition, also known as HCCI, or reacting charge compression ignition, known as RCCI, or it can be just generalized compression diesel combustion. On the other hand, we have the spark ignition SI strategy. So with the spark plug ignited strategy, we have the conventional spark plug, which has been widely used for decades. Some advanced engines have integrated multiple spark plugs to ensure combustion happens and misfire is avoided. Another alternative to the spark plug with promising capabilities is the pre-chamber, which we'll explore in the next slide. Here we can see the pre-chamber and the spark plug in detail. The pre-chamber itself is usually 2 to 5% of the entire cylinder volume, so you can expect a very small confined volume within this pre-chamber compared to the overall engine. The pre-chamber can be active or passive depending on how fuel is delivered. Active pre-chamber requires a special fuel feed system which directs the fuel inside the pre-chamber. The passive fuel pre-chamber, on the other hand, relies on the compression stroke to fill the pre-chamber with the pre-mixed fuel. The pre-chamber accommodates multiple nozzles which aid in the combustion phase, creating multiple flame jet fronts inside the main chamber, enhancing combustion performance and efficiency. The combustion process inside the pre-chamber is initiated by the spark plug itself. On the other hand, we have the ordinary spark plug, which we all know. This plug can initiate a flame kernel as programmed, and it can house multiple tips for multiple sparks at once on the tip. In these images, we can see the moment that the spark is initiated inside the pre-chamber, and then 5 degrees crank angle afterwards, which shows the combustion propagating inside the pre-chamber, and finally, around 10 degrees after the combustion, we can see the flame jets penetrating into the main chamber. Whereas with the conventional spark plug, the flame starts propagating as soon as the spark is initiated inside the main chamber and starts spreading around inside the main chamber. In here, we can see these 2 ignition strategies in action side by side. As we can see, the piston is undergoing its compression stroke. The color of the mixture is changing from dark to light blue as it's being heated by the compression. And now with the activation of the spark, in both ignition strategies, we see the combustion phase forming. As we see, using a pre-chamber initiates the combustion in a small confined volume and then guides multiple flame jets into the main chamber, penetrating through the unburnt mixture and initiating the main fuel to burn. The red-orange regions show the flame propagation and combustion phase throughout the region. Whereas with the spark plug, the main mixture starts combustion from the single source of ignition as the spark plug is activated. So we really rely on that single flame kernel to start ignition and to spread and to propagate the combustion throughout the main cylinder, creating the combustion phase. To conclude, we'll be going over the benefits of using a pre-chamber. Well, first of all, with the pre-chamber, we can achieve a faster and more stable combustion, and this is thanks to the presence of multiple high-energy jets penetrating into the main chamber, facilitating and optimizing the main combustion phase inside the main chamber. Secondly, the pre-chamber delivers a higher thermal efficiency because the pre-chamber itself can accommodate high pressure ratios. Also, with this technology, we can have improved lean burn operation, thus reducing NOx generation and other pollutants, as well as enhancing fuel consumption by burning lean. And perhaps one of the most important factors is the pre-chamber can easily be fitted just by replacing the spark plug. So this basically means minimum modification to the engine block or the cylinder head by swapping the spark plug with the pre-chamber. However, on the other hand, the pre-chamber itself is much more sophisticated and complicated, and of course more expensive compared to the conventional spark plug. Also, the pre-chamber may perform differently, meaning better or worse for different fuels. Thus, CFD analysis is extremely recommended to investigate to see if the pre-chamber is beneficial for a specific engine, or perhaps if the spark plug would outperform the pre-chamber, depending on the fuel, the engine geometry, and the operation. Thank you for listening. With that, we conclude today's short lecture. For any further discussions and questions, please don't hesitate to get in touch with us.